All right, this is our last section for this semester, section 4.5, integration by substitution. Just out of curiosity, how many of you are continuing into Calc 2? That's the plan for you. So what you will do when you continue into Calc 2 is you'll pick up right where we left off. Chapter 5 is more integration. In fact, the entire Chapter 5 is different integration techniques. But we are going to explore one integration technique in particular today, that way it'll give you just a little bit more breadth of being able to work with antiderivatives. A lot of language here at the beginning. I hope that you have your notes printed out so you don't have to write too much down. I want you to think about this function, y equals sine of x cubed minus 4x, and I want you to take the derivative. So in that blank spot, take the derivative of that function. Not the antiderivative, the derivative, okay? So write that down, and then we'll confirm it all together. Okay, what was the big overarching rule that you have to use on this particular equation? The chain rule. This is a chain rule problem, so I hope you recognize that. We are about to hit finals, and at the finals exam, of course, you'll have derivatives and antiderivatives all mixed together. So what did you get for your derivative of this function? Sine became cosine, right? What was in the parentheses? Right, x cubed minus 4x. So that's the derivative of the outside, and then you had the derivative of the inside, which was 3x squared minus 4. Good job. Okay, so this is the derivative. So what we're going to do today is we're going to actually be taking things that look like the right-hand side, what you just created, and going back to the left-hand side. Now, if you take a look at what's on the right-hand side, it actually looks like a product, right? I mean, it doesn't just look like one, it is one. And so you haven't been able up till now to take an antiderivative that looks like a product. And all products are not what we're going to do today, but some of them are, okay? So we're going to we're taking what's on the left-hand side, the right-hand side, my left, your right, the right-hand side, and moving back to the left-hand side. So one option when we're presented with finding an antiderivative that looks like this is to decide if there is a piece of it that looks like if you took the derivative, it'd be the other piece. Okay, yeah, I said that right. If the derivative is the other piece. So in particular, let me go back to the one we just looked at. We can identify, hopefully, that this piece, I didn't mean to mark through it, this piece and this piece have this relationship that one of them is the derivative of the other one, right? Okay, that's the kind of functions in particular that are going to work with this method that we're looking at today. It's where one piece of it is the derivative of the other piece. This x cubed minus 4x, the inside function, its derivative, 3x squared minus 4, is one of the factors being multiplied. So what we're able to do is we're able to do something called u substitution. So we let u equal the inside function, x cubed minus 4x. And then we take the derivative. So I'm going to use a notation that we don't use very often, but I need to use it for what we're doing this today. We usually like to do primes, right? Everybody likes primes, right? Prime, y prime. Well, in this section, we need to do our derivative notation that looks like dy dx. Since this is u, it'll be du dx. So the derivative, of course, of x cubed minus 4x is 3x squared minus 4. Okay? So that's du dx. And what I'm going to do is I'm going to move the dx to the other side like a multiplication factor, because this is how we're really going to do the problems. We're going to write down that du is equal to 3x squared minus 4x dx. Okay, so just move the dx to the other side. Everybody good with that? So here's the way that the problem would actually play out. If we were taking the integral of the cosine of x cubed minus 4x times 3x squared minus 4 dx. We do a substitution. We do a replacement. So this piece right here is what I'm going to call u. And this piece right here, all of it, whoops, didn't go very far. All of this is equal to du. Can everybody see where those pieces are? They're equal quantities. So this is like when you were working in an algebra course somewhere along the way and you were doing substitution, right? You were looking for two lines intersected and you solved one of them for the other one and then you plugged it in, right? That's the phrase people like. Yes, ma'am?
Where did the x come from on the or 3x squared minus 4x? Because you moved the x to the other side?
No, it's right here.
Okay.
It's actually part of the original question. Yeah, and where it came from is because I started with this side of the equation. So the 4x is actually inside the derivative already, or inside the sine function or the cosine function, depending on which we're looking at already. Okay, so what we're trying to do is we're trying to do a replacement of pieces so that the problem becomes easier. That's really what we're doing. So instead of what I previously had written, I can rewrite this as cosine of u du. I don't know about you, but cosine of u du, I can deal with that. That's pretty straightforward. If I gave you that one on your derivative quiz or your antiderivative quiz a couple days ago, you'd have been like, yeah, no problem, I can do that one, right? That one's easy. What's the antiderivative of cosine of u?
You squared over 12.
It's just like cosine of x.
Negative sine.
Close.
Positive
Positive sine
sine.
of x. Yeah, it's just sine of x. So this is sine of u, because u is my variable. Okay? But the problem started out with x in it, so the problem has to end with x in it. So I need to do one more replacement in the final step of putting the x back in place of where the u is. So what is u?
X cubed minus 4x.
X cubed, was it minus or plus? Minus, okay, sorry, I'm on the wrong page. All right, yep, x cubed minus 4x. And I was a little sloppy, we needed those plus c's, of course, so let me go back and put them on there. Okay? So that's where this process comes from. It comes from chain rules. That's really what we're doing. This is sort of like the reverse of a chain rule process, okay? Of course, not every problem that looks like a product is a chain rule, agreed? Some of them are like legit products. And there is another process for doing those kinds of problems, but that's in chapter 5, and we're not going to get there. So sad, I know. You're all disappointed. It's the only one we're going to do together. Okay, so let's take a look at some more examples of these so you can see how this works. So I've taught this section already to my business calc class. Theirs is a little bit different, of course. But one of the things that I had talked about to them is when you're identifying what the u is usually in one of three places. And it may be always. I can't think of an example where it's not, but I want to sort of give myself an out in case I'm not thinking of one, right? That's what I'm doing here. It's usually inside of a parenthesis, underneath, like in the denominator of something. That's a possibility. Or, what's the other one that I said? Oh, in an exponent, like an exponent spot sometimes. So an exponent spot or underneath a radical is all kind of parenthesis-like features. So while it's not really written here, we understand that, of course, that all of this underneath the radical is really inside of a parenthesis. Your calculator would require you to put it there, right? So when you're looking at what you might want to let u be, those are the locations to look in. Things that look like they're embedded inside of something else. And in particular, what I've put in parentheses in this blue is, in fact, going to be what u is. And the reason is because what happens when you take the derivative of 3 minus 4x squared? You get negative 8x, which is exactly what's out here, right? Yeah, so that's what we're doing. So we're going to take this piece, and we're going to identify what we have. So our u substitution step means that we let u equal something. So in particular, the u value that's useful and helpful for us here is to do 3 minus 4x squared. And then when we write this down, we're going to write down du equals, and we're going to take the derivative. So what is the derivative of 3 minus 4x squared? Yep, Jared and Kelsey now is also just, or Frankie's also just told me that it's negative 8x. And then there's the dx that I'm going to write on the other side with it. Okay, remember?
Hopefully use a different thing than x for these problems because you have to put the x in. Is that where you're using u?
Yes, exactly. We're changing the variable to u to use something different than x. Sometimes you'll see people change things into t's. I don't think t's are so great because some people's t's look like plus signs. U is sort of the standard for doing this that you see people use. So, yeah. So our step that's actually back helpful in the calculus antiderivative part of what we're doing is the replacement step next. It's what makes everything else easier. So I've got an integral symbol. I've still got my cube root, which we'll deal with in a minute. But underneath my radical now, what do I have? Just u. And then everything here at the back end is equal to what? Du. This problem is way easier to work with. Now it's still the cube root, which is not especially useful for how it's written. How else could I write it instead? Yep, u to the 1/3. So what is the antiderivative of u to the 1/3? Okay, so say it again louder. Good. Yeah, u to the 4/3. We add 1 to the power divided by 4/3. This is a little too thick. Okay. I need one more thing on there. No, not du. Plus c. Yeah, the du is one of the ways to think about it is that these two pieces mark sort of parentheses ends. This tells you take the antiderivative, and this tells you with respect to u. So when the antiderivative symbol, that script s at the beginning, goes away, the du goes away with it. Okay? All right. We can clean this up a little bit without even substituting back in x's. This can be written as 3/4, right? Instead of 4/3 in the denominator, it's 3/4. And then this would be the cube root of u to the 4th plus c. And that's kind of as clean as it's going to get. If you really wanted to write the u on the outside and leave cube root of u underneath, you could do that. But this is okay. We don't want u in the problem, though, at the end, because it didn't start out with u, right? It's what we call a dummy variable. We made it up to work with it. So we need to put it back the way it began. So in place of where my u is, I need to put in the 3 minus 4x cubed, and then the power of 4 there, plus c. Oh, it was squared, wasn't it? Sorry. Let me fix that. Thank you. Is that okay? Lovely. Y'all good? Okay, so we're going to keep working through these. Now, the reality is that they don't always look exactly like the du we expect. So, taking a look at this one, any thoughts as to what you might let u be?
Just what's in the parentheses be u.
Yep, what's in the parentheses, without the squared on the outside, just what's in the parentheses to be u. Lovely. So this is one of those sections where we're going to keep moving forward back and forth between derivatives and antiderivatives, right? So what is du going to equal? 4x to the 3rd. I need one more thing. Dx. So what's sort of concerning at the moment? Yeah, there's a 4 there that's concerning, right? There's not a 4 in my equation, or in my problem, right? It's not an equation, it's a antiderivative. There's not a 4 in it. So what did you want to do, Maurice?
I was going to put like a 1/4 into the actual equation.
Yes, you could do that. Another way to do it is to deal with it from here. So if we remove it or move it, rather, to the other side, and the way that you can write it maybe a little bit cleaner is like what you've just suggested with the 1/4 here, and it will be put into the equation then. So what happens is that my, my x cubed dx, which is in my problem, is going to be replaced with a 1/4 and a du. Okay? So it gets replaced by more than just du. So this piece right here is what? It's u squared. It's u and then it's squared, right? This piece right here gets replaced by a 1/4. You can put the 1/4 on top. You can put it in front. I don't care where it is. It's just going to be a constant multiplier. Just going to be part of the solution in a moment. And the rest of it's going to be replaced with the du. So there's that 1/4 and the du. And we don't have a denominator or quotient rule kind of process, but we do have the ability to rewrite this like this, right? So, what is the antiderivative of 1/4 u to the negative 2? Everything I circled in blue is this. So it gets replaced by the part that's in red. So these pieces are the part that's in red, replacing the part that had been in blue. Yep. Oh, there's finally clicked into place. There we go. Okay, everybody good? All right. What's the antiderivative then for 1/4 u to the negative 2? Good. Okay, so add 1 to the power, which would make it -1. Divide by the new power -1. You can put the negative in front if you wish. And then the cleaning up of this would have the u in the denominator, right? No negative exponents there. But we can't stop here because that's got u in it, our dummy variable. And I need to have the actual variable for u in the problem, which was 1 plus x to the 4th. I'm perfectly fine with the denominator, leaving it left like that. I'm not sure what WebAssign will do. Factored form is usually preferable because if you had something that could reduce with it in the numerator, you would continue to do that, right? But if for some reason WebAssign tells you this is no good, distribute it out and then you'll be fine, okay? But this problem. Does it look like a product? Yes. So there are times in my other class, as we've been working, and students have asked the question, well, how do I know when I use substitution? You know you use substitution because it looks like a product or a quotient. That's really how you know. So when it looks like a product, for what we're doing now in this chapter, this is your only other tool. Either algebra simplification or trig simplification, which we've already talked about, or substitution. So here it looks like we have a product indeed, and so we do need substitution. What do you suppose u should equal? Okay, so there's two okay, so I want to make sure that I mention this. So Frankie asked if maybe it should equal sine of the quantity, and it won't because I don't have the derivative of sine in the problem. But if I simply let it be the inside of what sine equals, then I'll be good to go, which is the x to the 4th part only. Because the other piece that looks like a product is there. And the reason I mention that is because if you did have, think for a minute, if you did have the problem, maybe I've got this later in the notes, I don't know, like this. These are the derivative of each other, right? Sines and cosines. Yeah, so in this problem, it doesn't look like I've got any parentheses anywhere. Like I told you some sort of heads up things and I gave myself an out. Here's my out. This doesn't happen in my other class. They're not doing trig. But the u substitution on this one would involve a sine function, right? U would actually equal sine because the derivative of sine's in the problem. It's cosine. Okay, so not our problem at the moment. Maybe it will be later. We'll see. For the moment, however, what would du be? What is number 4? Next problem. Fun times. What is it? 4x to the 3rd. And what else do I need? dx. And if I examine the actual problem that I started with, that whole thing is in it, right? Yeah. So the piece here and here is this piece and will be replaced by du. Sign was not changed because it wasn't part of the u substitution, so it remains. And then the x to the fourth piece will get replaced by u. So, what's the antiderivative of sine of u? Yeah, it's cosine of u, and it is negative. Of course, plus the c. And what will my final answer then be? Good. So negative cosine of x to the fourth plus c. And this is the problem I was basically talking about just a minute ago. I mean, it isn't, but it's going to be the same way. You'll notice that you have both sine and cosine in the problem, correct? You'll also notice, you also know that sine and cosine are each other's antiderivatives, yeah? I mean, derivatives and antiderivatives, they go back and forth. It's just this cyclic pattern between them. So which one would we have to let u be? I mean, what are we going to choose? Probably the cosine x. I agree with you. Maurice, why do you think that that might be a good choice? Because it's cubed. That's exactly right. There's another reason, too. Anybody know? Just because it's being cubed is not necessarily the only thing. It's also in the denominator. The fact that it's in the denominator is going to help us in making those decisions. Reminder to yourself, real quick, that the notation right here, of course, means that I have the cosine of x quantity cubed. So when I chose that u is actually cosine, that's why, is because the cosine will get replaced, the cubed will still be there. Everybody good with that? Okay, what is the derivative then, du, of cosine x? Yeah, it's sine x, and I heard a couple people saying negatives. Yep, there's a negative sine x in there, dx. Now, in my actual problem, I don't have the negative, correct? I mean, I don't. So when I do my replacement, I really have that I'm going to replace the sine of x dx with negative du. So I will insert a negative into my original problem as I do my rewriting step. There will be a negative there. So coming back over here then, here's the negative. I'm going to put it in front this time, just because you can. It's possible. The sine x and the dx, these two pieces, are going to be replaced by what? Du. So it's 1 over. I mean, there's still a 1 on top. It doesn't all of a sudden just disappear, of course. You know, we replace it with 1. And then the cosine of x is being replaced by u, which is still cubed. So instead of having u cubed in the denominator, how else can I write this? Right, u to the negative 3 du. All right, so I need an antiderivative of u to the negative 3. All right, so I have u to the negative 2 divided by 2, or times 1/2, like you said. There's my negative. Plus c, right? Okay, and then what did you have in mind to do, Maurice? Yep, the negatives will go away. If you wish, you can write this as 1/2, but I'm about to put my u squared back at the bottom, so I'm going to just leave it as the 2 in the denominator. And what would my last thing that I need to do be? Put it back in. Yes, this is 1 over 2 cosine squared of u plus c. If you leave it as cosine parentheses with a square on the outside, for me, that's fine. I don't care. But this is kind of cleaned up. Oh, sorry. Thank you. Not a u and x. You guys are keeping me on my toes today. I appreciate that. You bet. All right. We're going to change up a couple of things as we conclude our last few examples. So variations, not anything really different, just variations of what we've been doing. This one wants to find an equation for a function that has the given derivative and whose graph passes through the given point. So we talked about this with some different language earlier on. We talked about this being a specific antiderivative. We've got plus c's on the end of all problems, right? And we talked about the fact that the reason that happens is because when you take the derivative of the c, it goes away, right? C is just a number. So you lose some sense of location when you take an antiderivative. It could be shifted up and down and not change the shape of the graph because derivatives really just talk about shape. So the shape could actually occur anywhere shifted up and down. This problem is going to have us solve for c at the end and actually figure out what c is. It's going to fix it into a specific spot on our graph. So as we're taking a look at this, the whole problem itself is we'll just have an additional step at the end where we solve for c. So to start with, we are going to find the antiderivative of secant squared. So hang on. All right, so this is where we're starting. All right, I do have a U substitution here. It's not a very exciting or interesting one, but can you imagine what I should let U be in order to actually make this into one of the rules that we've had already? 2x, yeah. And the reason I say that it's not very exciting is because the derivative of 2x is not very exciting. It is simply 2 and then the dx, right? So it's really not a very exciting antiderivative because it doesn't give me anything that actually makes this original problem look like product. I mean, secant squared 2x does not look like a product, and most of the ones we deal with look like products or quotients. So this one sort of feels like it's, I mean, it's there, but it's really kind of almost not because the derivative ends up being a constant. And it's actually not even in my problem, is it? So kind of like what I was doing on the other problems, moving the 1/2 or the 2 to the other side, like this, so that I end up with 1/2 du equaling the dx is what will end up happening. So back in the original problem, a very clean 1/2 goes out front, and then I have the secant squared of u du. Okay, the dx at the end is replaced by the 1/2 at the beginning and the du that I now have at the end. What's the antiderivative of secant squared? Okay, antiderivative of secant squared was, what did you say? Sorry for my distraction.
X, tangent x, positive.
No.
Negative.
Nope. It's tangent x. Good try. Tangent of, in this case it's u, so tangent of u plus say c. The derivative of tangent is secant squared. I think you're thinking of the derivative of secant being secant x, tangent x. It's a little bit different one. But I know what u is. U is 2x, right? So this is actually 1/2 tangent of 2x plus c. And if this was called f prime to begin with, now this is f of x, right? As we've been working our way along. And we're going to solve for c. So how are we going to do that? Yeah, we're going to plug in that point. This point is an xy ordered pair. It tells me that the x value is pi halves and the y value is 2. So this is 2 equals 1/2 tangent of 2 times pi halves plus c. So this is that unit circle stuff that I reminded you to go back and refresh your mind on if you hadn't thought about it in a while. What is the tangent? This ends up being, of course, pi. What is the tangent of pi? It's 0, yeah. So this piece is 2, this piece is now 0 plus c, so c is 2, right? So my specific antiderivative, or the equation that matches this information about going through this specific point, is actually 1/2 tangent of 2x plus 2. I'm going to show you another one here that feels very weird. It feels very different than the ones we've done because of an extra algebra step in the middle of it. Yes, so sorry. Okay. I would say that this problem is the most difficult one that we're going to do today. Okay, so if you tend to write a little bit large, write a little bit smaller on this one because I know you've got half of a page, but this one's going to take several lines. Okay. We have talked about identifying you and things that are not you in a problem, and the identification that I have sort of indicated to you would indicate that what would you be in this problem? What do you expect it to be? Yeah, so it's either the x plus 1 or the 2 minus x. Which one do you think would it be? It is one of them, actually.
2 minus x.
It's the 2 minus x. Kind of like when we were identifying this one over here and we said, oh, look, I want it to be the cosine because it's cubed, right? It's got a power. Same idea here. I want it to be the 2 minus x because it has a power of 1/2. Okay? So I realize that this still is not going to look right for a moment, but just bear with me. I promise all will work out in the end. This is 2 minus x. And here's why it doesn't feel like it's going to work out. What in the world is the derivative of 2 minus x? It is negative 1 dx, and that is not the other piece of my problem. Agreed? It's just not. The other piece has an x out there. What am I going to do about that? Well, we're going to do a little bit of different stuff with some algebra. I'd like for you to take the 2 minus x, and I'd like for you to solve for x. If I solve that for x, what does x equal? That's part of it. I mean, yeah, well, close. I just want you to take this equation and solve for it. Okay.
Wait, solving for u or x?
It's already solved for you. I need it solved for x. Okay, we're going to subtract 2. Right? But then what do I have to do with a negative? I have to divide by negative 1, right? So x is going to end up equaling 2 minus u. Yeah? I know you don't know where I'm headed with this, but are you okay with the algebra part of it?
Yeah.
Yes? Are we good with that part now? That's what x is. X is 2 minus u. U is 2 minus x. Doesn't always work out so nice and symmetrically, but it does on this one. Are we okay? Okay. We are going to do a substitution step like we've done before, but we have this extra substitution here at the end that we're going to need. So hold on tight to that for a moment. The piece that's underneath the square root is going to be what? It is u. The du or the dx at the end is actually negative du, right? If I move my sign. So I've got my du at the end, and I'll put my negative out here at the front over here. Still good. Okay. The plus 1, also still good. Yeah, x is 2 minus u. It's just a replacement. Now, I kind of hope that at this point you're thinking like, that looks just as messy as it did before. And it really kind of does. But I want to show you why it's preferable. So let's clean things up just a little bit from where we are. I have 2 and I have 1, so that's 3. So this is 3 minus u. I have a negative out here in front. I have square root of u du. If you wish, I'm going to go ahead and do it. I'm going to distribute the u through the negative through, so this is now u minus 3 square root of u. The reason that this is preferable is because what's underneath the radical does not involve addition and subtraction. That's really why. What's underneath the radical is simply one quantity, u. So here's why that's useful. I can write it as u to the 1/2. And I can distribute it across the parentheses for u and the negative 3. So what is u times u to the 1/2? It's u to the 3/2. Can I take an antiderivative of u to the 3/2? Yes, I can. And then when I distribute the other piece, I have negative 3u to the 1/2. Can I take the derivative of u to the 1/2? Yes, I can. So the pieces themselves allow for the distribution because I don't have addition and subtraction underneath the radical. So let's take those antiderivatives. What's the antiderivative of u to the 3/2? Okay, good. So 2/5, that's the same thing as the division by 5/2. 2/5 u to the 5/2. And then I've got my 3 here. What's the antiderivative of u to the 1/2? Two-thirds, right? U to the 3/2. U to the 3/2 divided by 3/2 would be times 2/3. So that's a little bit friendly since the 3's will cancel. Oh my goodness, what a mess. It's still not very pretty. I've still got fractional exponents and I've got u's involved and I need to clean up some of those things before I can continue. So let's put the values for u back in next. And we'll worry about the cleanup in a moment. Or let me write it as square root of u to the 5th, actually. And I have 2 square root of u to the 3rd. And I should have had a plus c up here. Okay, u is equal to 2 minus x. So this is 2 over 5, square root of 2 minus x to the 5th, minus 2, square root of 2 minus x to the 3rd, plus c. Okay, is everyone okay so far? All right, this can still be cleaned up. I mentioned earlier on, let me find the problem, on this problem, okay, one of the earliest ones we did, the first one we did, in fact, that the fact that it had a power of 4 and it was taking the cube root, we could write it differently, and I said it really wasn't that big of a deal, and the reason I said that is because it didn't really help on this problem. If I do that on this problem, take a look at what's going to happen. I can take one of these out because it's 3 minus 4x to the 4th, and then I would have the cube root of 3 minus 4x. And do you see how that actually looks worse? Yeah, it does, right? So in some sense, it's very preferable to leave it here because changing anything else makes it look worse. There's more, it's more complicated than it was before. You could. It depends on if you're being, I mean, you can always make mistakes anytime you simplify things, right? Yeah, that's definitely possible. The difference on this problem is that these two pieces that I have here that are separated with subtraction, they can actually be combined if I go ahead and do what I just did on that last problem. If I actually pull out the parts that are able to be pulled out. So recognizing this, right, that 5/2 means 2.5, right? That's what 5/2 means. I've got 2 of these, so I'm going to pull out the 2 that are there, the squaring part, and I have 1 that's left underneath the radical, the 5.5. So I have the 2/5, and then, you know what, that's going to run out of space here. Let me make this a little bit smaller so we can work with it. So I've got my 2/5, and I'm going to have 2 of these, that's the squared part for the 2.5, with the half still underneath. And then the same thing over here, I have 3/2, which is 1.5, so I have 1 of them, right? This is like a power 1. And then I have the square root, the power 1/2, still as 2 minus x. With many things in your life, things get messier before they get better, right? This is that messier step. It will get better. If you notice, each of them have that 2, the square root of 2 minus x, correct? So it can be factored out in front, and we can combine what remains. So I'm going to pull it out in front. You can pull it out in back if you wish. And let's just see what's left. Oops, on my subtraction. So I have 2/5, 2 minus x squared, minus 2 times 2 minus x, plus c. I don't really like the 2/5 in there. How about you guys? You want to keep those 2/5? You want to distribute the 2/5?
Could you pull out 2 minus x as well?
Oh, we could. Yes. Thank you for that. Good point. Let me actually do that. One of them anyway, right?
One.
Yep. Yep. Good point. Yeah, I didn't do that on my paper that way, but that's a really nice step. We can do that. I have 2/5 times 2 minus x. That would be, oh my goodness, let's see. I have 2 minus x. I have 2 minus x here. And then we have 4/5 minus 2/5 x. Minus 2. What can I combine from that? At this point, I'm up here. So looking at those 3 values, what can combine? The 2 and the 4/5, right? Yeah, those are both constants, so those can be combined. What will they simplify to? Yeah, negative 6/5 minus 2/5 x plus c. So I want to show you several places where you could leave this, okay? This is okay. I mean, it's not bad. It's a little bit weird to have the fractional piece in there. If you didn't like the fractional piece, what you could do is you could pull a 2/5 out, especially if you were working with this and doing something else with it. So pull the 2/5 out at the beginning. There's my square root of 2 minus x. There's my 2 minus x. And then pulling out a 2/5 is actually going, in fact, why don't we pull out a negative 2/5 because they're both negative. It's going to leave me with 3 minus x plus c. I would say that that's probably the cleanest spot right there to leave it in. You could leave it right there. If for some reason you were solving this in a different way and you ended up actually having these two multiplied out, I don't necessarily think that would be bad. It would be a polynomial, right? It would actually be x squared plus x minus 6. That would be all right. In some ways, it's nice to leave it here because it's completely factored. So some different versions of it, but this is probably the cleanest one that's in there in red. Okay. All right. Couple of more things. What do you notice on numbers 7 and 8 that are different than the ones we've done before? They have bounds. Yes, they do. So we're going to do the problems exactly like we've been doing before. We don't need the plus c's, right? When we have the bounds, like on the quiz you just took for me, you don't need it with a plus c because it cancels out. And we are going to, there's 2 ways to do the problems, and I'm going to teach it to you just one way because I really do think it is the easier of the 2. If you know another option and you can do it effectively, that's great. But I'm going to have you change it into the bounds with you, like we're doing. We're going to turn things back into x, and then we're going to plug in the boundary numbers, okay? So taking a look at what we have here, what would you suppose that u should equal? Fabulous. 1 plus the square root of x. And if you want to remember to yourself as well that this is the same thing as 1 plus x to the 1/2, that would be helpful. What would du be for 1 plus the square root of x, or x to the 1/2? Okay, 1/2 x to the negative 1/2 dx. Now that particular form of it is not especially mirroring what was in my problem. So if I manipulate a little bit, I can see that this is 1 over 2 and 1 over square root of x, right? Part of that's in my problem, isn't it? Do you see it? That piece right there is the 1 over square root of x piece, and there's the dx at the end. If it helps, you could rewrite this to recognize that this is 1 over square root of x and 1 over 1 plus the square root of x squared dx. You don't have to rewrite it, but that is the truth. These are quantities that are equal. So I have this piece and this piece. What do I not have? I do not have the 1/2. So if I move it to the other side, what will it become? 2. So I'm going to have 2 du. Now what I'd like for you to recognize when I write my script S is I'm not going to put the numbers on top and bottom, because I'm in the process of changing things into u's. Those numbers were evaluations for x, not for u. So I'm just going to leave them off for the moment. So I'm going to have a 2, like we said, and the du. And then right here I'm going to have 1 over what? U squared. Or if you prefer, you can write it as u to the negative 2 at that point. What is the antiderivative of u to the negative 2? What is it? Close? Let me keep it with the negatives for a moment. It's u to the negative 1 over negative 1. Yeah. I still have a 2 out here in front. I don't need the plus c's, right? We already recognize that. So this is a negative 2 over u. That's how that cleans up. And u is, well, it's 1 plus the square root of x, right? And if I put a plus c on the end, we would have the general antiderivative. But that's not what I'm asked for. I'm asked for the definite integral, which means the evaluation at the points 9 and 1. But 9 and 1 are really nice numbers to put inside of square roots, aren't they? They really are. That's so friendly. How nice of the textbook to do that for us. All right, so I've got negative 2 over 1 plus square root of 9 minus negative 2 over 1 plus the square root of 1. Minus a negative is plus here at the end. Okay, so I have negative 2 over what? 4. Plus 2 over 2. This is negative 1/2 plus 1 for a grand total of 1/2. Okay. So again, it's just like everything else, right? This problem over here that we did here. It's all the same stuff. I just have this extra step at the end where I solved for c. All the same stuff. It's just have this extra step at the end where I plug in the values for x. So let's try one more and we will finish up for today. We had this happen before, right? Where it is u substitution, but it doesn't really very exciting, agreed? This piece doesn't even have that involved. It doesn't need anything about that. So what we're going to do is we're going to separate these two pieces because I don't need u substitution for sine x. But this other part, although it's not a very exciting or interesting one, it does have u substitution, at least in a sort of an unexciting way. Okay? So part of my problem, I don't need to worry with it. What's the antiderivative of sine of x dx? Negative cosine of x. Okay, so it's on its own. The other piece has the u substitution. So what would u be? (2x) and du? 2 dx, right? Again, like I said, it's not exciting. And so we can divide by 2 or multiply by 1/2. So this is really going to give me 1/2 integral of cosine of u du. Okay, constant multipliers just carry on to the next step. It's 1/2. What's the antiderivative of cosine of u? Sine of u. And u is, oops, 2x. Okay, everybody good with that? Okay, so that's all the same stuff. Put a plus c on it. We would be done if I did not have boundaries on this, right? But I have limits of integration. Draw my vertical bar at the end of pi and 0. So instead, now on this one, I have negative cosine of pi plus 1/2 sine of 2 pi, because there's a 2 in that particular part of it, minus negative cosine of 0 minus plus, what was it, plus 1/2 sine of, and it's 0 because 2 times 0 would still be 0. So let's find some of these. What is cosine of pi? -1, so I have the opposite of -1 here. What's sine of 2 pi? 0. I have cosine of 0, so negative cosine of 0. So what's the cosine of 0 part? That's actually 1, so the negative is coming from here, not from the cosine itself. And then the sine of 0 is 0, lots of zeros. So what do I end up with? Is it 2? I think it's 2. This is going to be 1, and this is going to be 1. So I end up with 2, and I'm done. Lots of zeros otherwise happening. Any questions? Alrighty.